Let's welcome them.
So before I get started, just a quick level check. How many of you have either heard of or used VMware? Okay, that's actually really good. Jennifer's been at VMware since 1999, so she was one of the original 12 developers, and I've been there since 2003. And the original genesis of this work occurred at ISCA. Not this work. The original genesis of this talk occurred at ISCA because I was sitting next to Suzanne at dinner, and I said, "Oh, where are you a grad student?" And she said, "I'm actually a faculty member." And having been totally embarrassed, then we talked a little bit more, and she does a lot of interesting stuff. And so we decided that it'd be cool if I could come and talk about what we did at this conference here at Sonoma State. So here I am. So I thought it'd be kind of interesting to give what I'm going to call the unofficial history of VMware. The original paper called Disco was written for a conference called SOSP and was published in '97. Okay. In 1998, the people that wrote that paper ended up founding VMware. My favorite story is that in 1999, we found out that Buddhist monks use VMware. It's a pretty funny story. So the deal is, there are these monks somewhere in Tibet and in some monastery, and most of the monks like to use Windows, but there's one monk that really likes to use Linux. And so he found out about VMware, they started using it, he sent a nice email to VMware saying, "I'm so glad you guys exist." So I'm kind of curious what those monks were using it for, but that's fine. And if you think I'm lying, there's a citation of the story, so there you go. In 2003, which again when I joined VMware, we invented live migration of virtual machines, so you can move a virtual machine while it's still running. I'll talk about that more later. And this led to a host of interesting innovations, and eventually, by 2008, 100% of the Fortune 100 used VMware. This was at 99% for a really long time, but we finally got Walmart to cave. So that was pretty cool. And now we're in 2010, 2011, whatever. The big buzzword is cloud. I promise I will only use that 3 or 4 times during this talk because, you know, I'm an engineer, not a business guy. So, okay. Now to get more further into the talk, the point is that if you look at the history of VMware, we see that virtualization is becoming a lot more commonplace. And the reason that happens is that it makes some things really easy, and I hope to demonstrate that throughout the course of this talk. And one of the things that it makes easy is that many of you are students, I imagine, and those of you who are faculty, you've probably never really walked into a data center and seen how painful it is to do a lot of the everyday things that you have to do. And when you use virtualization, a lot of those things become a lot easier. And so that's one of the reasons that virtualization is so popular. So what I thought would be interesting is we're going to talk a bit about the research that we've done, but I wanted to set it up by giving a retrospective as to how virtualization got from where it started, and from the Buddhist monks, all the way to working in data centers. And after that, we're going to talk about the crux of our paper, which is about virtualized data center management. And then we're going to make a bunch of forward-looking statements about what kinds of things we think would be interesting to look at and what are we already looking at. So no talk about virtualization would be complete without Butler Lampton's famous quote, "All problems in computer science can be solved with another level of indirection." And as I was digging this up, I realized that a lot of people ignore the corollary of that, which is, well, except for the problem of too many layers of indirection. So hopefully we haven't inserted too much of that stuff into our software, and it's actually pretty highly performant. So most of you are aware of virtualization from the point of view of the Java virtual machine and whatnot. We're actually going to focus on the system virtualization aspect, the bottom 2 bullet points on this slide. And I'm not going to talk much about our competitors and stuff. I'm mostly going to obviously focus on VMware and the sort of journey of VMware, so to speak. So where VMware, I guess, got started is thinking about a physical machine. And obviously a physical machine, yeah, it's got hardware. You know, it's got a bunch of NICs, processor, CPU, whatever. And the interesting realization is that resources on most hosts are actually vastly underutilized. And I'll get into that more in a moment, but the point is, if you think about physical machine, you've got hardware, so CPU, disk, whatever, and then you've got software, you've got some operating system, and you've got applications, and the operating system is basically tightly coupled to the hardware. I mean, maybe this dates me, but how many of you remember when, you know, a Mac was on a PowerPC and Windows was on an x86, and so, oh my God, there's this big religious divide and whatnot, so that's pretty bad. And in addition, what you see is that you have a single active OS instance running on this piece of hardware. So, okay, that's pretty vanilla. All of you use that, you use your laptops, whatever. Okay, now if you think about a virtual machine, you're taking this hardware picture and you're pushing it up a layer and inserting a virtualization layer on top of the hardware. So now you've put this software abstraction here. You know, this still looks like your laptop or your hardware. He has no idea that he's actually being fooled into running on top of a virtualization layer and running on actually totally different hardware from what he actually thinks he's running on. So, you know, he might think he's running on a 2 CPU machine, when in reality this big box has 64 CPUs and it's sharing it among a bunch of different instances. And that that's a full, this is a fully encapsulated, essentially sort of pseudo piece of hardware. And the virtualization layer is there as our extra level of indirection, not too many, no offense to David Wheeler. And we're decoupling now the hardware that this guy thinks he's running on from the actual physical hardware, which is kind of cool. And in addition, we're now enforcing isolation. At least, if you're kind of clever and kind of obnoxious, you would probably think of ways to do this. But these guys are fully isolated from each other. So it's a nice little sandbox where you can test things or another. They're not going to harm each other. So that's really what virtualization is. And I think, this is kind of an obvious picture. I think the takeaway point is that there are some actual formal requirements which were elucidated in this paper by Kopek and Goldberg back in '74, which sort of formalized what virtualization has to provide, namely fidelity, so it must act just like a physical machine. It's got to be performant. I went through and read the reference, and performance was, well, it shouldn't be that bad. Okay, that's not so good. But anyway, the point is, it should be pretty close to actual hardware. And then finally, it should provide safety and isolation. Like I said, you don't want those virtual machine instances to be able to read each other's memory and stomp on each other. And I know that most of you already know this anyway, but of course, VMware didn't invent virtualization. That was invented back in the 60s, as with everything else, by IBM. But virtualization on the x86 is the really new thing that VMware pioneered. Okay, so what I wanted to do, now you know we're all level set as to what I'm defining by virtualization. I wanted to go a little bit over some of the technical challenges of virtualization to kind of, again, give a little bit of a history lesson. Because a lot of times when people think about VMware, they think, oh yeah, I'm running Windows on Linux, or sorry, Windows on Mac in my case. What's the big deal? And I think they don't really get an appreciation for the fact that this is running in all these data centers and whatnot. So let's do a little history lesson. I should point out, this is of course a lecture by itself, and now that I'm on camera, if you want to invite us back, feel free. I don't mind coming to the wine country. There will be wine at lunch, right? But anyway. Okay, and I should also point out that this is not in any particular order, not necessarily chronological, and it's a very partial list of some of the technical challenges. Well, the first one, like I said, VMware pioneered virtualizing the x86. And in sort of technical jargon, it's not classically virtualizable. The simplest example of this is to say that certain operations run differently when they're in user mode versus privileged mode. Okay, so if you think about it, a naive way of virtualizing an operating system, you might say, well, I'll just run this hypervisor virtualization layer at the most privileged level, and I'll just run the OS below that. But the problem is, if that means that OS level operations perform differently than they would have performed if they were at the highest level, that's not a good thing. So a couple of clever guys went and patented ways of doing that, the founders of VMware. And in addition, what they also realized is you can't just virtualize the CPU, you also have to virtualize memory. Because I'm a VM and I think I have 2 gig of memory, but underneath there's actually 8 gig of memory on this actual box. So how do you do this mapping correctly, and how do you allow a lot of different virtual machines to use the memory underneath? Okay, step 1, make virtualization possible on x86. Step 2, if I were running my laptop and I were running VMware and doing I/O were really slow, I wouldn't have a viable product. So the next step is actually making I/O faster. So as a dumb example, I guess, one way to do this is to replace certain expensive calls with memory map calls. And another way to do this is to say, you know what, suppose I have 10 VMs. Suppose I get a network packet and I have to interrupt the VM that's getting that network packet. It'd be highly inefficient if every time a network packet came in, I go and interrupt that VM. But what if I have all these VMs being network intensive and every time they get it, blah, 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 blah. So instead, it's very interesting to imagine coalescing those interrupts and delivering them in one big block. And there's actually a paper that I'm citing here, which if you're curious, you can go through and read, that talks about a lot of the different ways it's made I/O faster. Okay, now where are we? Now I can run VMware. I can make I/O credible, so I've got a product. The next step is that if I really want to run a bunch of virtual machines on the same hardware, I have to make sure that if each of those virtual machines is configured to use 4 gigabytes, that I don't have to have 4 gigabytes for every VM running on this physical OS. Otherwise, I need a machine as big as this rack just to run a bunch of VMs, which seems utterly wasteful and pointless. So, Carl Walsberger comes along and says, you know what, let's do some memory resource management. Let's pioneer the concept of page sharing, which basically means that 2 different VMs, or even within the same VM, if they are using the exact same page, don't make the hardware allocate multiple copies of that page. Just use one page, and if anything ever changes, then it will use techniques like copy on write or whatever to make sure that they don't stomp on one another. So that's step 1, make sure that you reduce how much memory each VM needs. But step 2 is you're always going to have a situation where you have all these VMs running on the same host, and they're going to be contending for memory. So let's invent some interesting ways to have them coexist peacefully by I like to say this like this. I just invented this last week at some conference, where there are several ways to do memory management. One is the polite way, where I say, hey, you need memory and you need memory. Can you please give me some memory to give to this guy? And then the other way is like the mafia, saying, give me some memory, and I'm going to give it to this guy, and I don't care what you think. There's a lot of different ways to do that. They have different performance implications. A lot of them are detailed in this paper. Okay, so that was page one. So now we've got a viable platform that can run multiple virtual machines on the same hardware. Next step. This was when I joined VMware. I joined right after this happened. The deal is that many enterprise applications need multiple CPUs, and so the next logical step was to try to create virtual SMP virtual machines. And you can imagine there's a lot of interesting race conditions involved with this. I mean, if you have multiple virtual CPUs, you don't want one of them to be running while the other one is idle, especially if the idle one has a lock that the running one needs. Very, very bad. So you got to overcome a lot of interesting challenges there. Okay, now where are we? We can run enterprise applications that are multiple SMP. We can run a bunch of them on the same host. Gee, wouldn't it be nice if we could use shared storage? So we can, instead of having every host have their own local disk, have them all share a storage area network, or share NFS, or share storage. And that, you can always basically leverage off what's already existing. You can take whatever they have for Linux and create NFS clients or whatnot for our platform. But what we decided was, hey, a VM is basically a big file. So why don't we make a file system that is really tuned for doing operation on big files? And thus was born VMFS. Again, a lot of clever people did it, and there's a patent. Okay, now where are we in this journey? I can run a bunch of applications. I can use a big shared storage. Those tend to be highly reliable, highly available, a lot of value-added features. The next step is to say, gee, I've got this shared storage. And we have to run enterprise applications. Well, enterprise applications need really high availability. So let's go ahead and think of ways to improve availability. And that's where vMotion, that's not necessarily where vMotion was born. I think it was more like, this is a cool idea, let's do it. But anyway, it ends up being a very valuable thing. The idea is this. You've got a bunch of hosts that are sharing a storage infrastructure. And if I have to take down one host to do maintenance, and it's running virtual machines, well, it would be very bad if I had to turn off all those virtual machines, fix those, and then turn on the virtual machines. So instead, what I can do is I can move those virtual machines while they are running, fix the first host, and then move them back. And that's all enabled by having shared storage and a lot of the other features I've described. And there was a paper written here. This is interesting. The paper was written in 2005. It was productized in 2003. And the interesting thing is some of our competitors have written papers which are cited more frequently because they came out at about the same time, even though ours was in our product 2 years earlier. So that's kind of interesting. So since this is YouTubing, I'm not going to try to... The competitors are good, no worries about that, but we're better, so fine. Okay, finally, now AMD and Intel come into the game back around 2005, 2006, and they're saying, gee, virtualization is a big market, let's add hardware support. So they add hardware support, and now the death knell to VMware. People are like, oh, you don't need VMware anymore, just blah, 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 all this nonsense. Which is pretty much nonsense. Interestingly, there was a paper written by some people, maybe it's biased, it was from VMware, but the point is, the initial versions of hardware support for virtualization tackled part of the problem. They said, well, we know some aspects are difficult, let's attack those. And it was great that they attacked those. Those became easier. For example, if certain instructions behave differently, whether they're running user mode or privileged mode, we had to jump through a lot of hoops to make that work. And if you can do that in hardware, that becomes faster. But the little issue of sharing memory between virtual machines was not made faster. It was a generation 1 version of the product. And if you look at the types of things that are involved in that, it turns out that the software that we had written was still faster than running hardware virtualization. So the point is, this is gradually changing, and now hardware virtualization is obviously very viable, etc. But the point is, initially, it wasn't, and so we still had to use all of our software and all of our tricks to make it work. Okay, last slide for technical challenges before we move on to the meat of the talk. So the deal is this. You've got shared storage. You've got VMs that can move anywhere. It seems like a good use of this would be in load balancing. For example, if I've got this one host that's really, really busy, and I've got this host that's sitting there being lazy, why don't I move the VMs from this host over to this lazy host so that we can balance the load a little bit? And we have automated ways of doing that. It's called distributed resource scheduling. It measures CPU and memory, makes a lot of automated decisions about when to move virtual machines around. Okay, and if you're familiar with this, basically the way to think about it is that an individual virtualized host, the CPU scheduler there uses a proportional share scheduler. This distributed resource scheduling, which works across hosts, extends proportional share resource scheduling across hosts. It's kind of cool. You're upping the levels of abstraction. So now you're sitting around, you're running enterprise applications. You can move them whenever you want. You can run VSMP. the next logical step is to think, well, some people don't just want to be able to move something quickly, but they want something to never go down. And thus was born fault tolerance. Now, fault tolerance is, again, a lecture in and of itself. There's a lot of different challenges that are perhaps not obvious when you're thinking even something dumb like I've got a single uniprocessor virtual machine, and great, I can run it, I can record all the interesting activity like interrupts or whatever, and make sure that it's replayed on some other host, on some other VM. So those VMs are more or less in what we call V-lock step. But the deal is now if I have multiple CPUs for a given virtual machine, the problem becomes, frankly, exponentially harder, a lot more difficult with respect to what sort of events you have to tag, etc. So there are a lot of interesting technical challenges required to do that. Well, okay, we're almost at the end of our journey. We've got photons, got all these things. Now, back in 2003, 2004, one of the big things was simultaneous multi-threading, and that's when basically Intel said, you know what, you've got a single core, but you've got a bunch of logical threads on that core. They'll share the underlying resources. And frankly, I thought this was dead a couple of years ago, but they brought it back when they brought back Nehalem. And in doing so, they did it better, but they also created a whole host of interesting CPU scheduling and memory problems. One example I'll give is that if you've got a single core and multiple threads that are sharing that core, you might think, gee, it'd be really good if those threads were sharing the compute resources because they can share a cache. But then you might think, but gee, they're sharing the same compute resources. What if they need to do exactly the same thing and one of them has to block because the other guy needs that resource? Like, what if they're both floating point intensive and I only have one floating point resource? So you have to trade off a lot of different other things. In addition, there's this concept that now I have NUMA hardware. In other words, it's more expensive to grab memory from this guy's node than it is to grab it from my node. So that introduces a lot of scheduling issues because you clearly don't want all of your memory to be on this guy's node. Okay? Finally, the last thing I'll talk about is this brief overview of technical challenges of virtualization. It has to do with the fact that we've talked a lot about CPU and memory. I've got this host. He's very busy. This host is totally lazy. Let's move some of the VMs from this host to this host. However, that was considering CPU and memory. There's a whole issue of storage, right? If this guy has a VM that's really cranking on the storage subsystem, wouldn't it be nice if this host did not get locked out because this host was so greedy? So you need some sort of ways to proportionalize the usage of storage. And so we've come up with a lot of different solutions for that. And there's a paper in FAST 2010 that talks about some of that interesting stuff. So what I hope you've seen is the journey. VMware started on something kind of like this, and now works in a data center. And what we observed in the data center is that with the increasing use of x86 servers, and the observation that, first of all, most data centers have a one application per server model. Okay? In addition, most servers are grossly underutilized. Maybe they're running on average 5 to 10%. So if every time you need to do some sort of prototyping or development, you have to buy a new server, and every time you do that, you're basically only going to use 5 or 10% of it, it's a complete and utter waste of time and money and a lot of other things. And it's also very expensive to maintain. So it turns out this is the perfect use case for virtualization and what we call server consolidation. What does server consolidation mean? It means that you take something like this, actually from a customer site, and you convert it, ta-da, to something like this. Literally 300 servers sitting around, blah, 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 to one rack with VMware. Pretty cool. And as far as like making things easy, well, we already made things simple by making you maintain a single rack versus a bunch of racks. A lot of times, one of the big things as students I don't think we appreciate much is that there's this concept of operational expenses, or OpEx, right? Where, if you have to maintain a bunch of servers, that's just one rack is way less expensive to maintain than 10 racks because it's just more hardware to screw around with. And so anytime you can shrink how much hardware you're spending and how much power you have to put into your data center, how many cables you have to run, that's all making things simpler. But virtualization made things even simpler. I talked about this concept of vMotion or live migration, where you have a virtual machine that's running on a host, and we can move that virtual machine to a different host. Now imagine you've got the enterprising system administrator. He says, geez, I got this entire rack, and I really have to do maintenance on that rack. Why don't I just move every virtual machine to this other rack? Now imagine the analog in a physical world where you've got a bunch of applications running on these physical hosts. Well, there's no natural way to encapsulate, without, support within the application, there's no natural way to just easily migrate that application to a different host. So this makes that kind of stuff incredibly simple. Of course, the deal with that is that it makes things simple. But now you're in a position where you have to say, you know what, I'm doing all these great virtualization, I'm using all these great virtualization added benefits, but I do have to use them judiciously. The theme of this talk is what are some of the challenges that you encounter as you increasingly use virtualization in the data center. So basically for the rest of this talk, what I'm going to try to say is that virtualization management is a new workload. if you think about, let's take an application. Let's take Word. What does Word do? Well, besides making you aggravated, what Word does is it eats CPU, it eats memory, and it eats disk. Well, what do you do when you do virtualization management? You move stuff around, you consume CPU, you consume disk. Sounds like an application to me, just at a higher level, and that's what I'm going to try to demonstrate. In addition, we're going to discuss how the fact that you've got these different ways of doing things that make things incredibly simple, they create different workflows in the data center, and those different workflows actually impact how you would design that data center. And finally, for those of you, I guess, that are students, maybe a lot of this stuff is going to be interesting. Maybe you want to read more, discuss more, work more, do projects, whatever. So, for the rest of this talk, we're going to talk about data center management, some of the challenges, and then move forward into the kinds of things we hope people will look at in the future. So, I'd like to start talking about virtualized data center management by first motivating it with physical data center management. In a normal data center, what you've got is you've got a bunch of hosts, one application per host, okay? And there's a system administrator who sits in some room with a big screen, and that big screen is connected to a bunch of monitoring servers that tell it, okay, these hosts are up, these hosts are down, maybe this network is congested, whatever. And a lot of the information there is archived in some sort of database so you can look at it later and figure out what's going on. So that's a physical infrastructure. In contrast, a virtualized infrastructure looks pretty much the same, but now you'll note that if we had one application per host in the physical environment, in the virtual environment, now we've got one application per VM, and we have beefier hosts. And between the VMs and the host, we've got a hypervisor there for that level of indirection. Otherwise, it's pretty similar, right? Now, the trick is you've got multiple virtual machines per host, so the actual number of applications that you can run in your data center can be quite large. So it introduces a lot of problems with scale. For the rest of this talk, I'm going to be talking about data that we collected. And these numbers are kind of dated, but we basically took a look at 20 to 25 customer sites, thousands of hosts, and tens of thousands of virtual machines to try to figure out how do people use our stuff. Okay, so at this point, we understand the basics of what management is. Let's talk about some very common operations so we can understand what cost they impose or what challenges they incur. So let's think about a clone. This is one of the most common operations. You want to take a VM and you want to make another copy of that virtual machine. It's actually pretty simple. You just take some disk image of that virtual machine, make another copy of it, and then put it on another host. So now we've got two copies of this virtual machine. That's a clone. You run some customization script to make sure that they have different IP addresses and whatnot. Okay? So that's clone. Another common operation is snapshot. I don't know how many times this has saved my bacon. Okay? When you do a snapshot, you checkpoint a VM while it's running, and then you change something, and if it works, great. If it doesn't work, you can revert back to that checkpoint. So to give you an example, I'm starting with this VM, and I know I want to install the latest Windows patch. So I take a snapshot, it's my golden VM, and I take a snapshot of that virtual machine. Exact same as the original virtual machine. The next thing I do is I go ahead and I modify the guest operating system. Maybe I install a patch in Windows. I'm happily cruising along with that patch, and then all of a sudden, boom! As with Windows, well, I shouldn't say this since it's being taped, but sometimes things happen. So your thing crashes and you're kind of screwed. But you're not screwed, because you were smart. You took a snapshot. So you revert that snapshot to your golden copy, or rather to your snapshot. Okay, so that's snapshot revert. Very, very popular and unique to virtualization. Now, of course, there's the other alternative, which we hope is what actually happens, which is that you're cruising along with your modified guest, and actually nothing happens. So instead of having to revert the VM to its original state, what you can do is actually remove that snapshot. You don't need it anymore, and start running with this new virtual machine. Okay, so that's the snapshot workflow. Okay? Finally, the last thing I'll talk about is very simple. This happens in every data center. It's often you've got a host and someone says, I need another network adapter because I have to attach to some other network. So they got to pull out the host and stick some card in and get screwdrivers and junk like that. In a virtualized environment, this is way easier because you know what? I press a button, boom, another disk on a virtual machine. Pretty nifty stuff. I, of course, ignored things like power operations, which in some sense are fairly intuitive, and I already went through vMotion, so we get it. So at this point, I'm hoping that we actually understand what types of things people do in a data center. Now let's understand why these are challenging. Well, the first thing is that there's an issue of quality of service. To make an analogy, imagine if you're using Microsoft Word and it's really slow. You'd probably get pretty annoyed. Okay, I know I do. So now, imagine you're a multinational corporation and you tell your IT admin, I want to change all the mail servers, and you have to change them between 6 p.m. and midnight because that's when nobody's at work. Okay? If you can't finish it between 6 p.m. and midnight, you're going to disrupt basic business functioning and business critical operations. So you've got this fixed time window. And so getting these management operations done quickly is actually really, really important. Okay? Another thing I want to point out is that this is VMware. We accommodate enterprise applications. And by enterprise applications, I'm drawing a distinction between what I'm going to call a cloud-based app and an application in a cloud. A cloud-based app would be something like Google Search, right? You've got some applications running over your entire infrastructure. They have complete control of the application, the OS, etc. Versus an app in a cloud, the example of this, maybe you're using TurboTax, right? So you log into the web, and TurboTax is on some server. You have no idea what, but it's some enterprise application that's running on some currently existing platform, and it's running on Windows and whatever, okay? So the point is, with enterprise applications, you actually have to deal with a lot of issues that you don't necessarily have to deal with if you've written the entire application from scratch. And another interesting thing I'd like to point out is that because we're doing this consolidation play where you've got multiple virtual machines on the same host, well, if you had an application that was I/O intensive and now you're consolidating them onto a single host, well, now you're going to have a lot of I/O going through that host. And so you might be changing the calculus of what sorts of resources you end up using. Okay, so now we understand the primitives, so to speak, of what people do in virtualized data centers. Now let's look at some examples of actual data centers to see what people have used our stuff for. Here's a great example. So I was looking at this customer stuff, and what I do is on the x-axis I show time, and on the y-axis I show the number of tasks that the administrator was performing. I've highlighted two specific tasks because they were the most common. One is automated load balancing. So our software is sitting around saying, okay, this host is lazy, let's give him some VMs. The other one is snapshot revert, which I've already described. What we see here is that there are periodic bursts of automated load balancing, and there are also very periodic bursts of snapshot revert. Okay, you can see the little spiky things for the snapshot revert, and you can see the big bumps for automated load balancing. Let's focus on 1 2-week period. Okay? In this 2-week period, the workflow actually becomes quite a bit clearer. What you can see is that at 2 a.m. every Saturday, it's got to suck to be that guy, but anyway, at 2 a.m. every Saturday, they're doing a bunch of snapshot revert operations, right? In addition, at 2 a.m. every day of the week, it's got to suck worse to be that guy, you're doing live migration operations. What's actually going on is this. Here's what's happening. It's a multinational customer. They teach a training course around the world. Once a week, they snapshot their, so they start a class by running from a golden virtual machine. They do the entire class, and so people can make whatever changes they want to the VM, and then at the end of the week, namely every Saturday night at 2 a.m., they revert the snapshot back to their golden copy. Now, it turns out the reason they take a snapshot every week as well is that they might be making patches or whatever in off intervals. Why are they doing the 2 a.m. live migration? Well, again, they're not doing that. That's all automated. What's happening is that at 2 a.m. is their maintenance cycle, and so while that's happening, our software is smart enough to say, gee, that host needs to be maintained. And you've told me it's going to be maintained. So I'm going to move the VMs off that host so that you can maintain it and there's no downtime. Okay? So we kind of see what this workflow, what's happening and what the workflow is. Let's take another example. This is called boot store. Okay? One of the common uses of virtualization is something called VDI, or virtual desktop infrastructure. The idea is this. Instead of, you're an employee at a company, instead of giving you a big desktop, what I do is I give you a very small, thin client, and I give that thin client a connection to a virtual machine that's running in some data center. Okay, so now the sysadmin only has to administer the data center, he doesn't have to administer to you. Problem. Every employee comes in at 9 a.m. and they want to turn on their virtual machine. Okay, well this is going to cause a huge load on that data center, and that's what's called a boot storm. And you can see from this example that between 8 and 9 a.m., we have this huge burst of people powering on their virtual machines. So the question is, what impact does that have on your underlying infrastructure? Well, I'll give a little bit of I'll talk about that a little bit later on. The final case I'm going to talk about is what I'm going to call after-hours maintenance. We have an IT department over a few weeks. Here's what it looks like they're doing. Again, number of tasks is on the y-axis and time is on the x-axis. It looks utterly random, but it's actually very controlled. Every night between 6 p.m. and midnight, they're sitting around and doing administrative tasks. They're rolling out new virtual machines, they're changing their mail servers, they're doing whatever. The point is, it has to occur between 6 p.m. and midnight, and not only that, there's actually quite a large degree of concurrency here. What you see is that they're doing about 20 to 40 tasks per hour, so maybe they're upgrading 20 virtual machines per hour or whatever, And I'd like to point out that maybe in a physical environment, that might not be as easy to do, because it's obviously a lot more difficult to go into some data center and unrack something and pull out cables than just to sit at your cozy little desk with music in the background, a glass of wine, and press a button. But the point is, 20 to 40 tasks per hour is a non-trivial amount of work to be done, and it has to occur within their maintenance window. The kinds of operations this IT administrator were doing, they were doing power operations, they were rolling out some new software, they were snapshotting VMs, testing the software, and then either removing or reverting the software. They were doing a lot of clones because they create a golden image and then they wanted a bunch of copies of that golden image. Okay? So, to give you an appreciation of how common these operations actually are, what I've done is I've created a table for, and this consolidates a lot of the information across all the data centers that we looked at. And what I'm trying to demonstrate in this table is, first of all, I give the name of the operation in this column right here. Okay? Next, I give the average number of operations per day. In other words, if you just took a look at the total number of operations they did and divide it by the number of days, what would you get as on average per day? That can be misleading. So instead, what I did is I took a look and I said, well, actually, what was the peak number of operations they did on a given day? Okay? And what this illustrates is that actually management operations are incredibly bursty. I mean, the average, 2 a day, whatever, it doesn't matter. But what they're actually doing is like 700 on one day. That's a pretty big deal, and you have to be aware of that, because if they have to get those 700 done within 1 hour, you better have the resources for that. Another thing to point out is that there's a lot of operations in a virtualized data center that, of course, have a direct analog to a physical data center. For example, powering on and off VMs is kind of like powering on and off hosts, and same thing with resetting. But the frequency is a lot higher. It's very simple. I can imagine it's very simple to turn on 1,500 virtual machines in a day. I've done it myself. But I can imagine it's probably quite a bit more difficult to power on 1,500 physical hosts in a day. That ends up being quite a bit more difficult. Finally, I want to point out that in a virtualized data center, of course, you have all the value-added operations that virtualization provides, like live migration and some very snapshot revert operations. Okay, so now we set up the stage. We know what people use virtualization for, and we know that it can be very bursty, etc. Let's analyze what challenges this causes. To do that, let's first take a look at what data centers look like or are going to look like. What I've done here is I've taken several different configurations, I've called them small, medium, large, and feature, and I said, well, let's assume we have these many hosts in a rack. Okay, this is based on both engineering constraints as well as talking to customers in our own IT department. Then I said, well, you know what, let's assume we have 32 cores per host. This is a pretty conservative, well, it's pretty standard for this year and next year. And then let's assume that we've got 4 virtual machines per core. Again, it's conservative, and it's actually based on customer data. The bottom line of this entire table is that in the near future, an average rack, a medium rack, is going to have over 2,000 virtual machines. Now, to put that into perspective, when I joined VMware, a rack at the high end would have maybe 300 virtual machines. Factor of 10. Also, imagine if you had a physical rack, you wouldn't have 2,000 servers in a physical rack. I mean, that's 40 is like the maximum you're going to get. So, interesting increase in density and in scale. Well, we've made the observation, it's not in this paper in this talk, but we've made it, that the number of management operations you do is related to how many manageable entities you have. In other words, the more VMs you have, the more operations you're likely to do. Not only that, the more operations you do, well, clearly, that means the more resources you're going to consume. So this is why when I say management itself is a workload, it's because you're doing all these operations, they scale with the number of virtual machines, and they consume resources. Sounds like a workload to me. Okay. So let's talk about what resources they consume. If you think about vMotion, what vMotion or live migration is doing is it's moving a virtual machine from one host to another. So what it does is it creates a shell of a virtual machine. It copies the memory from the initial virtual machine while it's running over to the other virtual machine. So that memory is still changing, and so we have to keep track of that and keep moving it over and over. And at some point we decide, you know what, we're going to stun the virtual machine, we're going to checkpoint its state, copy it over to the destination, and once we've copied it over to the destination, we can go ahead and switch the disk for that virtual machine, so it's going to be pointing at the new host. Start play, boom, now the virtual machine is running on the second physical host. In that process, the most resource consumptive part is copying memory from the source virtual machine to the destination virtual machine. And that occurs over a network, so now we have to care, gee, how much network bandwidth have I have if I'm going to do these operations a lot? Next operation. Oh, and let's codify that a little. If I want to do that for one virtual machine, great. Imagine I want to do that in a minute. Okay, that's 130 megabits per second, so you can get away with a 1 gig switch. Imagine I want to do it for 4 virtual machines. I probably don't want that to take 4 times the amount of time. That's going to be kind of wasteful. So let's be generous and say that I want it to take 1 minute. Well, now you've just quadrupled how much bandwidth you're going to need in your network. And before you think, oh, he's just making this up to make things look difficult, for any number I tell a customer you can get things done in time X, they're immediately going to come back and say, get it done in X divided by 2. So I'm not making this up, these are real. Now finally, think about the enterprise administrator you mentioned at the beginning that wanted to do that for an entire rack. Well, all of a sudden, we're obviously not going to do that in a matter of minutes, we're going to do that maybe in an hour, and now all of a sudden you need a 10 gig switch just to handle your management traffic, because you need to get that stuff done so you don't disrupt your business. Pretty much the same song and dance applies to other operations. If you power on a virtual machine, the most amount of time you're spending is reading the image of that virtual machine from disk, and so you're consuming a lot of disk bandwidth there. Okay? And to give you an illustration, if you wanted to do that, say within 10 seconds, maybe you'd need 20 megabytes per second from your storage subsystem. We're assuming that when you power on a VM, you only need about 200 megabytes of that VM before you can actually start running it. This is based on data that we've collected. So okay, you want to do that in 10 seconds, 20 megabytes per second. If you want to do it for a rack, you know, you're going to need a 2 gig fiber channel switch just to do powering on of your virtual machine, just to start your business up in the morning. Final example is reverting a snapshot. Remember, reverting a snapshot is basically saying, oh my gosh, I installed a patch, it didn't work, let me roll back to where I was before. So the way you do that is that you pause the virtual machine, you've already saved all the state on the storage, so now you're going to read that in, and then you're going to resume this virtual machine. And it turns out the largest contributor to state is memory. So if you want to, again, do that for one virtual machine, okay, great. Suppose you want to do that in half a minute, 30 megabytes per second, great, a local disk could do that. But you know what, if you want to do that for your entire rack, same old song and dance, geez, you're going to need an 8 gig fiber channel switch, which by the way, is kind of expensive. And so, something to think about. Okay, so let's be a little more precise now about mapping the resource usage to the various workflows. If you're doing a snapshot revert, what I've done here is I've shown a graph of how many resources you consume if you needed to get all your snapshot reverts for a rack done. In red, it's 30 minutes, and in blue, it's 60 minutes. Now, I'm not going to drown you with data here. The bottom line that I want to tell you is that for a medium rack, you're going to need some amount of storage. And interestingly, if you take the applications that are running in that rack, okay, and you say, you know what, this is management. What do the applications themselves consume? Well, you can map some IO-intensive applications, and you can see that now the management traffic is more or less on par with the application traffic. And the bottom line, the green line, shows slightly less IO-intensive applications. So the point is, applications and management are taking on par a similar amount of resources. Okay? If you do the same thing for the boot storm case, remember every employee comes in and turns on their virtual machine, you know, same chart applies. You can basically see that you're going to require some amount of resources if you need to do it within like 15 minutes versus doing it within a half an hour. And if you map that to the application needs, you can see that it's again on par with the application needs. Now, the way I like to think about this is imagine, I don't know if you use Linux or Windows, imagine you're using Windows and you go to the task manager and you see that your operating system is taking 60% of your resources. Okay? That's resources that you can't use for your application. You're probably pretty pissed off, right? Well, think about the data center management as the operating system for the data center. Similarly, you know, maybe you're looking at this and saying, gee, it's only 40% of the resources. And maybe you're looking at it and saying, my God, it's 40% of the resources? Are you kidding me? You know, this is just to make sure things are functioning. That shouldn't be the case. That's why these things are kind of important. Okay. And for after-hours maintenance, I show a table where I show the various operations, what they rely on. The bottom line to take away from this table is that the resource demands vary quite a bit, from as little as 1 megabyte per second to as much as 360 megabytes per second. The point is, again, 360 megabytes per second is a non-trivial amount of traffic to be putting for stuff that's just making sure your system is up and running. And to sort of summarize all this data, I put for various different of our workflows, I compared the management traffic in blue to the application traffic. And you can see that the management traffic is either on par or greater than the application traffic. So we have to care about how we create networks and storage. And this leads us to how to design a data center. Well, there's a lot of different technology choices that you have to make. Do you want to use a SAN? Do you want to use a storage area network versus network attached storage? Do you want to put all your storage in one rack, or do you want to distribute it throughout your data center? Do you want to use a fabric that sends network and storage over the same wire because it saves cabling? Can you do that given the confines of the workload? Do you want to use SSD, solid-state devices, in order to reduce the amount of traffic that actually go out of the box? You know what? You still have to back it up, so that's only postponing the issue, not getting rid of it. In addition, What about the CPU? Maybe you're Google, and maybe you could say, you know what, just give me the cheapest CPUs and the cheapest memory. It's going to fail, and my application can tolerate it. But then again, maybe you're VMware, and you say, you know what, I'm running Exchange, SharePoint, SAP. Last I checked, they can't make the assumption that the hardware underneath is failing all the time. And so we have to build in the mechanisms to tolerate those things. And one way to alleviate stuff like, and by the way, if you just use the cheapest CPU that'll fail, it's probably not the highest performance CPU, which has all the virtualization-related bells and whistles. So there's a couple of different trade-offs that you deal with there. And there's also policy choices. Like I said, if you've got applications in management, do you want them running on the same network, or do you want them on different networks so they can be isolated? And you also want to figure out, well, gee, I keep showing numbers that say management's heavy, but management is bursty. Maybe I don't really care about management in general, just when it matters. And so we've written a couple of papers on that, and one paper is listed here. But the point is, why not create management when you need it? So I've divided future work into 2 slides. Yes, 2 minutes, 1 minute per slide. I timed this. That's what you can learn, students. Stay in school. No, I'm just kidding. Okay, so if you want to look at virtualization management, a lot of the issues that we've talked about have to do with performance isolation. Make sure that management and applications don't conflict, and make sure applications themselves don't fight each other. In addition, there's a lot of different use cases out there. We've got customers that have a data center in Cambridge, Massachusetts, and a data center in Palo Alto. They want to make sure that if Cambridge goes down, that it can be restarted in Palo Alto very quickly. Or you've got customers that have employees in Bangalore, in Europe, and in Chicago, and you want to make sure that you always have resources up and running for each of them. You also want to make sure that if you want to do additional testing and figure out before you actually deploy, you need benchmarks for that kind of thing. And finally, like I said, maybe you want to go in a completely different direction. Maybe you want to take a page from the Facebooks of the world and put all of your data and key value stores in memory and alleviate some of the issues with storage. As far as virtualization, and one final point on this slide that I wanted to make is people often look at management and say, you know what, it's bursty, but who cares, it happens once a day. Let me give you an example of why that's a bad way to think about it. Imagine I'm in Germany, and I have customers in Germany and in Chicago. In Germany, when it's 9 a.m., maybe in Chicago it's 2 a.m. I don't quite know the difference, but let's say. So, 9 a.m. is when all of my employees come in, and there's a boot storm on this data center. Great, a lot of storage traffic, but whatever, I can tolerate that for an hour. But now imagine the same administrator is thinking, gee, it's only 2 a.m. in Chicago, nobody's in the office, why don't I go ahead and do all of my backups then? The problem is if these are using the same data center, you now have these 2 geographically distributed needs which are pounding on the same resources. And that's why scheduling management operations is actually so difficult. It's a huge problem. Now that was virtualization management. If you talk about virtualization, one of the directions that we're moving in is mobile virtualization. To give you an example, plenty of people have their iPhone or whatever, but then when you go to work, they give you a BlackBerry. Well, people don't want to have to carry 2 devices, or that's kind of a pain. So wouldn't it be nice if you could unify the 2 and have a virtual machine that encapsulated your work personality? In addition, I talked a little about virtual desktop infrastructure. The big play here is people are very cheap. They want as many desktops as possible on a single host. Now, that introduces issues because you've got all this, if everybody's using their little small client and going to a virtual machine, well, that network pipe has to be big enough that I can actually interact with it, that my video and my audio is valid. And those are actually pretty deep questions. Finally, the big buzzword, I promise I'd only say this 5, I think I'm at 2, really good. Cloud computing is a pretty big deal for us these days, and one of the things that people are looking at is how to self-scale their application. I don't know how many of you have heard of Animoto, but there was a company that, they make this website that can take still pictures and make some movie out of it, and they got so popular because somebody posted it on Facebook that within the span of a week, their servers got 10x oversubscription. And so the ability to quickly spawn new servers and the ability to self-scale their application is pretty valuable. In addition, you want to do self-healing. If something is going wrong, figure out that it's going wrong proactively, move stuff around to accommodate that. And finally, probably the biggest thing is resource management. Like I said, we tend to focus on CPU and memory, but I/O, storage, networking, a lot of these things are incredibly important, and we have to consider the cross-product of them. For example, maybe 2 gigabytes of memory is important for this VM, and so I need to give that to him. But maybe for this VM, 2 gigahertz is important. But what if I don't have either of those? What do I do with these virtual machines? So the conclusion, virtualization is pretty awesome. There's a lot of very interesting research questions involved with it. And when you're designing a data center, you're going to use virtualization. You're going to make a lot of things easy, but make sure you use it wisely. And make sure to be cognizant of the challenges involved. That's it.